Alright, so this is part 284C3M1b7c8e13c9c6d3p38d19d7b22. It's line 22f1fa19c3m1b7c8e13c9c6d3p38d19d7b22. X-ray Photoemission Ois Spectra, part 7, 5G Wow Seti. There's the alien radio signal. And this is about photoemission energies, algorithms, and keyword research WOW data. So data continues from previous video, and it was part 6. So there's several videos in front of this one if you want to start at the beginning. Just backtrack. So it's X-ray Photoemission Ois Spectra part 6. Okay. March 15, 2013, when I did the Google search, I found a bunch of PDF files, and I put them into separate things. And when I get to line 27, I'll do a cross-reference with the words water, vapor, and long-distance communication. So the X-ray Photoemission Spectra, March 15th, that came from Googling Ti-sapphire laser and thin-film beam splitters. Then we went to passive optical network, and then radio frequency over glass. Then I added steam and vapor to that, and I got water, vapor, plasma treatment of glass surfaces, and then back to the X-ray Photoemission Ois Spectra. Quote from Wiki, Theoretical aspects of XPS. Quantum mechanical treatment. When a photoemission event takes place, the following energy conservation rule holds. And now my winds are getting up to about 70 kilometers an hour because the trees are really bending out there. I have to keep an eye out for tornadoes, right? So, if you see me dashing under my desk and the film's still rolling, I think I'll just like turn the camera so you can see. You can hear the wind, it's just a howling out there. So, sorry, I was doing that all night. We had hailstones this morning too. So, where HV is the photon energy, there's a little equation there. Okay? Another little equation is the electron BE with respect to the vacuum level prior to ionization, and E is the kinetic energy of the photoelectron. If reference is taken with respect to the Fermi level, as it is typically done in photoelectron spectroscopy. So we talked about electrons, we've talked about kinetic energy, photoelectron energy, Fermi, how to split a Fermi particle came up in line 22 several videos back, and now we're working on spectroscopy. So there's another equation, must be replaced by the sum of the binding energy B relative to the Fermi level, and the sample work function. From the theoretical point of view, the photoemission process from a solid can be described with a semi-classical approach, where the electromagnetic field is still treated classically, while a quantum mechanical description is used for matter. The one-particle Hamiltonian, which we've also discussed as well in line 22, for an electron subjected to electromagnetic field is given by, and there's an equation there. I look at the H, I think of the Higgs signal, that's electric field, right? Where V with the line through it is the electron wave function, A is the vector potential of the electromagnetic field, and V is the unperturbed potential of the solid in the Coulomb gauge, which of course we've covered in WOW as well. And then there's another equation, the vector potential commutes with the momentum operator, more equations, and so that the expression in brackets in the Hamiltonian simplifies to a big long equation. Actually neglecting another equation, term in the Hamiltonian, we are disregarding possible photocurrent contributions. Such effects are generally negligible in the bulk, but may become important at the surface. The quadratic term in A can be instead safely neglected, since its contribution in a typical photoemission experiment is about 1 order of magnitude smaller than that of the first term. In first-order perturbation approach, the one-electron Hamiltonian can be split into 2 terms. An unperturbed Hamiltonian with an equation plus an interaction Hamiltonian, another equation, which describes the effects of the electromagnetic field, which is a bigger equation, and H to me spelled out Higgs. In the time-dependent perturbation theory for harmonic perturbations, the transition rate between the initial state of V with the line through it and a little I, and the final state of V with the line through it with the little f, is just expressed by the Fermi's golden rule. So there's the equation for the Fermi golden rule, where E with the little I and E with the little f are eigenvalues of the unperturbed Hamiltonian in the initial and final state respectively, and HV is the photon energy. So we are discussing photon energy to use as a way of powering a UFO spaceship that flies without using fuel off of Earth. It uses airlifts. There are airlift formulas, different types of winds that you can use to lift this ship up off the ground and get it into outer space. And basically you wouldn't use your fuels until you are up there flying around. And then also there's recyclable fuel where you never burn out a fuel, which is interesting. And that's come up in the Wow data in line 22 as well. So lots of interesting things in line 22. So the Fermi golden rule strictly applies only if the perturbation acts on the system for an infinite time. Since in a real system the interaction has a finite duration, the Dirac delta function, which has come up before too, in the equation must be replaced by the density of states in the final state. And then there's this big long equation here. In a real photoemission experiment, the ground state core electron Be cannot be directly probed, because the measured Be incorporates both initial state and final state effects, and the spectral line width is broadening owing to the finite core hole lifetime. And there's a little tiny symbol there in brackets. Assuming an exponential decay probability for the core hole in the domain, and there's another little equation. The spectral function will have a Lorentzian shape. We've covered that. With a FWHM full width at half maximum, I think it's a T, given by, and there's another big equation, kind of a math equation type deal there. So we have X-ray Photoemission Ois Spectra still in the next video. I think there's a couple more to go. Okay, thanks for watching.